We analyze column-normalized Ulam matrices on a twisted boundary grid. Epsilon is strictly locked at 0.70 and resolutions to 8192 and 16384 cells. Here, paper 53's baseline for the WBA kernel showed the leading eigenvector, V sub 1, acts as a perfectly frozen delta spike. The anomaly appeared immediately below it. The second eigenvector, V sub 2, contained a geometry that researchers labeled dark matter. Beneath that rigid, perfectly motionless vertical column of the leading tier, the second tier contained a fluid mass violently rippling in place. The math behind this visual is highly specific. The dark matter is an ultra-localized packet of mass that carries massive, high-frequency oscillations. The prevailing numerical folklore attributed this behavior to a localized artifact. It was assumed to be an isolated quirk of the specific kernel being used. Specifically, researchers hypothesized that the extreme oscillation was caused by the heavy O1/y mathematical tail inherent to the WBA kernel. The proposed solution was straightforward. Switching the boundary grid to a kernel with a lighter tail should naturally restore numerical stability to the subdominant tiers. If the dark matter geometry is an artifact of the heavy WBA tail, swapping the underlying kernel will cure the deep spectrum pathology. To test this, we swap the WBA kernel for the Lorenz-Dean kernel. The Lorenz-Dean kernel acts as the designated safe baseline because it possesses a much faster O1/y² decay tail. This defines our diagnostic markers for spatial concentration. We track K90 for cumulative mass width, how many cells hold 90. Looking at the surface layer, the leading tier where J equals 1, the Laurentian kernel performs exactly as expected. It confirms its stable B1 classification. In an immediate reaction, the localized mass collapses instantly into a single point and locks firmly into place on the flat mathematical plane. The V subscript 1 measurement is a literal single-cell delta spike. The K90 width is exactly 1, and the top 1% mass returns a perfect 1.0. Extracting the spatial mass data for the second tier, V subscript 2, shows a similarly tight footprint. Its absolute mass collapses into a space 2 cells wide. If we evaluate only the spatial footprint of the mass, the Laurentian kernel appears to have eradicated the deep strata instability, but the mass-only analysis hides the full geometry. We have to look at the signed values hidden inside that 2-cell compacted footprint. Despite occupying only 2 cells of absolute mass, the signed Laurentian V subscript 2 sequence harbors thousands of rapid sign changes. To understand the true extent of this geometry, paper 54 executes a deep spectrum scan. We extract the top 10 eigenpairs to test how far down this localized oscillation goes. Moving swiftly past the perfectly stable surface layer, we descend directly downward into the deeply fractured subdominant strata. This table displays the empirical mass distribution results for subdominant Lorenzian tiers from J equals 2 to J equals 10 at a grid resolution of 16,384. Look at the K90 column. Every single value across all deep tiers collapses strictly into 1, 2, or 6 cells. The top 1% column corroborates this, maintaining a perfect 1.0 lock all the way down. Absolute mass concentration is an absolute rule. But every deep tier wider than a single cell carries massive sign change counts, ranging from over 3,000 to nearly 3,200 flips. Testing at the lower grid resolution of 8192 validates the exact same scaling. The entire spectrum is spike-dominated. There are no fat support eigenvectors anywhere in these 10 tiers. The Laurentian kernel does not cure the deep spectrum instability. It is completely consumed by it. We can now place the new Laurentian baseline directly against the historical WBA data from paper 53. This table shows a strict 2-row comparison between the two kernels at the second spectral tier, locked at 16,384 resolution. Their spatial footprints are indistinguishable. Both yield an identical 2-cell eigenpacket containing 100% of their mass within the top 1% of the grid. And both kernels exhibit extreme oscillation. The WBA kernel produces roughly 3,800 sign changes. The Laurentian kernel produces over 3,000. Despite their underlying mathematical differences, both of these distinct structures result in parallel, hyperdense, aggressively vibrating packets of mass. This gives us proposition 4.1. At the level of finite grid diagnostics, the deep eigenpairs of the WBA and Lorentzian kernels operate exactly the same way. The lighter tail of the Lorentzian kernel does not erase the pathology. It simply shifts where the instability resides within the deep strata. The dark matter eigenpacket is a structural failure of twisted boundary Ulam matrices at the B2 spray point. It is entirely kernel independent. We must apply strict guardrails to these findings. All observations in paper 54 describe finite grid phenomena. These discrete gap proxies do not represent thermodynamic phase transitions at infinite resolutions. They are completely walled off from the established continuum theory. The certified spectral gap and BV regularity results proven in paper 37 remain completely untouched by the structural failures of this specific boundary grid. But for ongoing boundary grid research, this failure changes our operational baseline. Specifically, standard theta probes are now compromised at epsilon equals 0.70. These probes require eigenvectors with wide fat support mass distributions, large K90 widths, to extract meaningful spatial diagnostics. Because the Lorentzian deep spectrum collapses down to mere single-digit cells, running a diagnostic probe here only reads empty buckets, producing artificial shadow data. This spike-dominated geometry now serves as our null calibration baseline. For future spectral probes to work, we have to hunt for fat support eigenvectors either much higher up in the subdominant tiers or transition to entirely new discretizations.